In this section, we're going to look at the flexure behavior of reinforced concrete members. We're going to look at the moment curvature behavior, the nominal behavior, and then the plastic and ultimate behavior of members in flexure. By the end of this section, I want you to be able to draw and label a typical moment curvature diagram for reinforced concrete members, explain how the rectangular stress block approximates actual beam behavior, and identify cases where approximations can be inappropriate, construct a simplified moment curvature diagram, describe energy absorption and energy dissipation, calculate the curvature ductility for a given section, either singly or doubly reinforced, identify the primary ways to increase ductility in a singly reinforced section and state limitations to each, list and explain the benefits of using compression reinforcement, use reconnaissance beam, a software or an Excel sheet based software to construct moment curvature diagrams, describe how confinement will affect moment curvature behavior, calculate short and long-term deflections using ACI 318, calculate plastic rotations, deformations, and moment capacities of a reinforced concrete beam. Our reinforced concrete members aren't just going to have axial loads as we looked at in the last several sections. We can also have transverse loading, for example, beams. These members will have either distributed loads or point loads, which will cause moments, curvature, rotation, and deflections. We can remember that our moments can be related to our curvature and our deflections using our different mechanics relationships shown here. And we're going to first look at how we can relate our moment to our curvature for the behavior of our reinforced concrete members. Shown here is a typical moment curvature plot for a non-pre-stressed reinforced concrete beam. When we first apply load, our concrete is going to be uncracked, so our concrete and our reinforcement are both going to be inelastic. At some point, we're going to reach the cracking moment, which is the moment required to cause cracking in our beam. At this point, we're going to have some inelastic curvature that happens, or deformations that happen as the force is transferred from the concrete to our tension steel. Then we're going to have another linear elastic zone, and it's in this point where our concrete's cracked in tension, but our concrete and steel working together will still be linear elastic. We'll continue in this range until either our steel yields or our concrete reaches around 70% F prime C. At this point, our concrete's cracked in tension and our concrete and steel are both inelastic. So then we'll need to use either the actual stress strain behavior or an approximation for the stress strain behavior until we find our ultimate moment, and then after we reach our ultimate moment, our member will fail. We can use the uncracked transform section properties in our initial linear elastic uncracked section. Then we can use our cracked transform section properties when we are in this second linear elastic zone where our concrete's cracked but our steel isn't yielded yet. And then, like I said, we either need to use the actual stress strain behavior or some kind of other approximation after we have yielding of our steel. In this first example problem, we're going to develop the moment curvature relationship for the section shown here. It's a 12-inch by 20-inch rectangular beam with an F prime C of 4 KSI, grade 60 reinforcement, so our yield strength of our steel is 60 KSI. We have 1.5 inches cover, number 3 ties, and 3 number 8 bars as our longitudinal steel. In this example problem, we're going to find a number of different points in our moment curvature plot. So we want to find our curvature before cracking, our curvature after cracking, so our points A and B shown here. Then we'll find somewhere our moment on our curvature at some points in our the second linear elastic range after our concrete's cracked, but before our section starts to go inelastic. Then we'll have a point D when our steel yields. And then we'll have a couple different points. So when epsilon C equals epsilon C naught, when epsilon C equals epsilon C usable, when our steel enters the strain hardening region, and then finally we'll find the ultimate strength of our section using the actual stress-strain relationships. In this example, we're going to use Hognestad's curve for our stress-strain relationship for our concrete, and we're going to use a full stress-strain curve for our steel. This means for our steel that we're going to have a linear elastic up until we yield. We'll have our yield plateau up until we start the strain hardening, and then we'll use a curve to represent our post-strain hardening behavior for our steel. You can pause the presentation now or mark where we are in the video and go and view the video for our example problem 1, and then come back to this presentation. Here's a table showing a summary of the curvature and moment values for each of these points that we found in this example problem. And this plot here is all the points in the previous table plotted. So our moment versus curvature for all those different points that we found in this example problem. We can see that the moment curvature relationship is almost elastic plastic. So we'll see later that we can use an elastic plastic approximation to approximate our moment curvature behavior for reinforced concrete sections. Next, we're going to look at the rectangular stress block approximation in reinforced concrete beams. We saw before that it's difficult to use the exact stress-strain relationship for concrete in the compression region of these members. Our compression stress region, however, is going to have a specific shape and an area and a centroid. So we can use equilibrium to find the size of the compression member, just setting our tension steel force, ASFY, equal to the concrete stress integrated over the depth of the compression block. We can approximate the shape of the compression block with a couple different factors. Our K1, our K, and our K3 we can use to approximate the shape. We need our approximated shape to have the same area and the same centroid as the exact shape so that we can get the same moment. So that'll be the goal, is to get the same centroid for our shape in the same area. And then we can sum our moment about the centroid of the compression region to find the moment capacity of the section. Testing was done by Hognestad, Rusch, and Maddock back in the 50s and 60s on the specimen shown here, where we have a tension force being applied and the shape of the compression block being observed. And they use this test setup to determine the different K factors in the equations that we saw on the previous slide. So they used the compression force to calibrate K1 times K3, and they measured the moment to find and calibrate K2. So this is how the different K factors were developed for the rectangular stress block approximation. Shown here are the different experimental results by Hognestad, Rusch, and Maddock for the different expressions. So for our K1 times K3, we can see how the experimental results line up next to the ACI value, shown as the dotted line. And for our K2, we can see how the K2 at the flexural strength lines up between the experimental results and the ACI value with the dotted line. We can see there's pretty good agreement between ACI and the experimental results. As I said, all of these experimental results were used to calibrate the different constants used in the rectangular stress block approximation. Here are those calibrations. So we have our K3 equal to 0.85. So the magnitude of our stress block is always 0.85 F prime C. We have our K2 equal to beta 1 over 2, which gives us the depth of our compression block, beta 1 C. And then we have our K1 value is just our compression force divided by K3 times F prime C times B times KD. And we will use these three K factors when we use the rectangular stress block approximation. The next thing that needed to be calibrated was the strain at the maximum compression fiber, or EC max. So through experimental testing, they related the extreme fiber strain at flexural strength compared to the compression strength of the concrete. And you can see that an ACI value, which was chosen to be 0.003, does a pretty good job of splitting this data in half. So ACI uses an EC max of 0.003. The shape of the specimen is going to affect what EC max can be achieved. So using EC max for rectangular sections is okay, but the strains and strengths, they vary if we have T-sections or triangular sections or different shaped specimens. So here are some results from Rucha's work. And you can see that with a rectangular section, we have a concrete strain of 0.003. If we have a T-section, we'll get a lower strain in our extreme compression fiber. And if we have a triangular section, we'll actually get a bit of a higher strain in our extreme compression fiber. So you can see the shape of the beam and the cross section is going to affect what strain is used in the what strain should be used in the extreme compression fiber. For ACI, we're always going to use 0.003, but you can see the effect of the different cross section shapes. Next, we're going to talk about the simplified moment curvature diagram that we can produce. Producing the complete moment curvature diagram that we did in the previous example was very complex and is unnecessary for the level of detail that we need. We can get away with 4 main points. We can first find the immediate before cracking moment and curvature, immediate after cracking moment and curvature, the end of the elastic region, and then our nominal capacity using our rectangular stress block approach. For our immediate before curvature, we'll use uncracked transform section properties to determine the stress when our concrete tensile strength is reached on our bottom fiber. Immediately after cracking, we can use our cracked transform section properties and our cracking moment to find our after cracking curvature. Then we can find the end of the elastic region by seeing when our cracked transform section properties will give us our steel yielding or our concrete reaching 0.7 F prime C. And then finally, we can use the rectangular stress block to find our nominal moment and nominal curvature. We will next look at an example problem where we're creating a simple moment curvature plot for the section shown below. Here we have a 16-inch wide by 24-inch deep rectangular reinforced concrete beam with 4 number 9 bars in tension. Our F prime C is 5 KSI, and we have grade 60 reinforcement with number 4 ties. You can pause this video, keep track of where you are, and then go to our example problem 2 video. On the next 2 slides, we're going to use our cracked transform section properties to develop a direct expression for the neutral axis depth and moment. So this is a simplified expression for representing our beam's behavior in the elastic region. So essentially what we're doing is through equilibrium, we're determining a factor for K with respect to a modular ratio and a reinforcement ratio. So if we have our modular ratio and a reinforcement ratio, then we can determine our K here. We can then use this K factor to determine the moment. So essentially, we'll set up our stress distribution, knowing that we're in the linear elastic range. We'll have a linear stress in our concrete. So we can find the centroid of this triangular section is just KD over 3 from the top. So the centroid of our triangle is 1/3 from the top here. and use that to find our yield moment. So this is a simplified expression to find our yield moment based on a K that we can find using our modular ratio and our reinforcement ratio. We're going to use this simplification in several derivations that follow, so that's why I'm introducing it now. But in general, just use the simplified procedure that we went over in the previous example problem. It's a little more straightforward and transparent than using these expressions here. We're next going to talk about two different ways that we can measure the ductility of our system. One is called energy absorption and the other energy dissipation. So energy absorption and energy dissipation are both important measures because they tell us how our load can redistribute in our structure. Energy absorption is the amount of energy the system can take as it's being loaded. This is the area underneath our moment curvature diagram. So this area underneath our moment curvature diagram. The energy dissipation, on the other hand, is the amount of energy the system dissipates during cyclic loading. So how much energy does it absorb? How much does it dissipate? And this is the area contained by the moment curvature diagram considering the hysteresis loop. So the area contained within this hysteresis loop here would be our energy dissipated in the first cycle. If we assume elastic plastic behavior, we can simply calculate our energy absorption and energy dissipation as shown here. So our energy absorption is just the area of this triangle underneath our moment curvature diagram plus this rectangular section, which I find here. Then our energy dissipation is the same area as our energy absorption minus the area of this triangle here. So you can see we have our energy dissipated through our system, through our rectangular beam here, and our energy absorbed here. We can also introduce something called curvature ductility. And this curvature ductility, which is mu sub phi, is just our phi max divided by our phi y. So our maximum curvature divided by our yield curvature. And curvature ductility is a way that we can quantitatively represent our ductility in a section. We can use curvature ductility to explore ways that we can increase the ductility of a section. So here we have our curvature ductility is equal to our phi max divided by our phi y. So we know our phi max is equal to our EC max divided by our KD max, or the distance from the neutral axis to the extreme compression fiber. And our yield curvature is equal to epsilon y divided by our D minus KD y, or the distance from the neutral axis to the centroid of our steel, and epsilon y being the yield strain. So we can simplify this and plug in values that we know, such as our KD max is just equal to C from our rectangular stress block approach, and our epsilon C max, the extreme compression fiber strain at ultimate, we'll take as 0.003 using the ACI assumption. We can remember how we found C, how we found rho, and our K equation that we found earlier as our elastic approximation here for our K. And then we can also remember our yield strain is just equal to Fy over Es. Here we can substitute all those given values that we know that we looked at on the previous slide into our expression for our curvature ductility. And we can simplify and make this substitution, which is a reasonable approximation. And then we'll find a simplified expression for our curvature ductility related to our steel stiffness, our reinforcement ratio, our modular ratio, beta 1, F prime C, our concrete compressive strength, and our yield strength in our steel. We can use this expression to approximate our curvature ductility, but when calculating our curvature ductility, it's better to calculate it exactly just by finding our max curvature and dividing it by our yield curvature. What we can do for this exercise, though, is we can use this approximate expression to see how the different variables affect the ductility of our section. So we can see that first, if we decrease our rho, decrease our reinforcement ratio, will increase our curvature ductility. Decreasing rho will ensure that our steel is yielding and our ductile steel is further on the yield plateau or in the strain hardening region. So that'll mean that we have an increased ductility. We can also increase ductility by increasing our F prime C. But note that when we increase our F prime C, our beta 1 is going to decrease slightly. So this is going to offset that benefit. And then finally, we can decrease our Fy to increase our curvature or curvature ductility. But note that decreasing Fy is going to impact our strength. So most of the time, if we decrease our Fy, we'll need to increase our As, which would increase our rho. So this can hurt us sometimes. So we can see that there are limits to each of these approaches, which we'll explore on the following slides. So here we're going to look at the effect of decreasing rho. We can see that decreasing rho is going to help some, but it won't help too much. So we'll suppose that we have an n equal to 8, so modular ratio equal to 8, which is a reasonable approximation. And we're looking at here the effects of reducing our reinforcement ratio from about 1% to half of that value. So you can see that our new reinforcement ratio related to our old reinforcement ratio, our new curvature ductility related to our old curvature ductility with the two reinforcement ratios will give us a ratio of about 2.28. So we'll get about 2.28 times the curvature ductility if we reduce our rho in half. So we get a pretty good gain, but remember that we're going to have a minimum reinforcement ratio that's allowed via ACI, and we'll also need a certain amount of steel to be able to provide enough strength in our section. So these two limiting factors will limit the benefit that we can get from decreasing our reinforcement ratio. On this slide, we look at the benefits that we can get from increasing our F prime C. Here, we're normalizing all of our curvature ductilities by the curvature ductility of a concrete compressive strength with 4 KSI. So as we increase our compressive strength, note that our beta 1 decreases. So our beta 1 times F prime C is going to increase, but not at the same rate as F prime C because of our decreasing beta 1. You can see that if we increase our F prime C 2 times, we only get an increase of 1.5 times of our curvature ductility. And again, this is an effect of our decreasing beta 1 decreasing the efficiency of increasing F prime C. So this is one of the limitations of increasing the compressive strength to increase your ductility. Decreasing the yield strength of the steel will work, and it will be quite effective at increasing your ductility. You can see that our Fy is in our denominator, and we have it's squared, so that'll improve the benefits gained here. As you can see, if we go from a grade 40, if we go to a grade 40 steel instead of a grade 60 steel, we'll increase our ductility by curvature ductility by about 2.25. You can see that this will greatly increase our performance, but it can lead to some problems related to, or one problem can be service level cracking, and the cost of grade 40 steel is about the same as grade 60 steel right now, just because grade 60 is so widely available. and grade 40s, not as available for reinforcement. So it can be economically disadvantageous. And again, similar problem to our reinforcement ratio, we still need to provide enough strength in our section. So decreasing our grade of steel, which decreases our yield strength, can often lead to more steel being required to satisfy other design limits. So if modifying our reinforcement ratio and our F prime C and our yield strength of our steel don't allow us to increase our ductility, how can we increase our ductility? The most effective way to increase our ductility is to add compression steel. Adding compression steel will improve the ductility of flexural members. We're going to look at how it improves the ductility of these flexural members using the same expression that we did before with our curvature ductility, relating our max curvature or curvature at ultimate to our yield curvature. And we're going to assume here that our compression steel is yielded. So just note that when we're using or this equation that we're going to derive assumes that our compression steel is yielded, which is often not the case. The first thing that we need to do is determine our compression block depth, and we'll do this through equilibrium, setting our tension equal to compression. In tension, we only have our tension steel, ASFY. Again, we're assuming here that our tension steel is yielded. And in compression, we have our same compression block component, and now we have the additional component of our compression steel, AS prime times Fy. Here, again, assuming that our compression steel is yielded. We can simplify this and solve for C, which is our unknown. We know everything else. And then use this C in our curvature ductility expression. Just note here that this expression is going to be different if your compression steel doesn't yield. We will simplify our derivation by using the same elastic approximation as we did before, our same K equation that we found before. Note that this isn't exact, but it's only going to be about 10 to 15% different for doubly reinforced sections. So it's reasonable to use here in just our approximate expression. We can then substitute our K and our C and all of our other known values into our curvature ductility expression to get this equation here. And you can note that adding compression steel is going to directly increase our curvature ductility. If we add compression steel, it'll affect our reinforcement ratio for our compression steel here, which will decrease our denominator, increasing our ductility. You can see that we don't need to play with our longitudinal steel at all, or our concrete compression or our yield strength. If we just add some compression steel, we'll increase our curvature ductility. And this is the most effective way of increasing our ductility. You can note here that this equation would suggest that we can get infinite ductility if we have equal compression and tension reinforcement ratios. Note that this isn't the case because as you increase your compression or the amount of your compression steel, it'll be more likely that the compression steel doesn't yield, which will affect the underlying assumptions that we used to derive this approximate equation. On the next few slides, we're going to step through some other advantages of having compression steel in our structures. The first is that it's practical for continuous structures. Here, if we have a continuous beam in a multi-bay moment frame structure, at the ends of the beam, we'll need top steel to resist negative moment. And at the middle of the beam, we'll need bottom steel to resist positive moment. We need to continue the reinforcement a certain length in order to develop the steel and also to meet some of our other ECI requirements for developing our shear reinforcement. So just in a continuous structure, we'll have doubly reinforced sections along the length of the member. So we might as well take advantage of our doubly reinforced section and the improved behavior that it provides. Next, we can see that adding compression steel will improve our serviceability performance because it helps to control creep and shrinkage. When we don't have compression steel, our long-term deflections are going to occur in the section, and they're going to be restrained by our steel in the bottom. This means that the top of our section experiences unrestrained creep and shrinkage, and the bottom restrained creep and shrinkage. So this will magnify the deflection that occurs in the section. When we add compression steel, the top compression steel is also going to restrain our long-term effects, our creep and shrinkage. So this is going to mean that our top has restrained creep and shrinkage and our bottom has restrained creep and shrinkage. So there won't be that, or there won't be as much of a magnification of our long-term effects due to, I guess, differential restraining in the section. Adding compression steel also provides a safety under moment reversals. If we design for load in one direction, it'll cause moments in our section. So it may cause positive moments, in this case, in this joint, which we can resist using our positive moment reinforcement. But if we have a load reversal, so in this case, a lateral load in the other direction, we can get negative moments at the same location. So providing our compression steel will allow for these moment reversals to be able to be handled by our section. And in this case, maybe this would be an expected moment reversal, but in some cases, you can have unexpected moment reversals. So providing the compression steel can help against those unexpected moment reversals that may happen. Adding compression steel, as we've been mentioning, improves our ductility in our section, but it also will increase the energy absorption and dissipation within our section. So here is a moment curvature diagram, a simplified moment curvature diagram for a singly reinforced and a doubly reinforced section. You can see that the doubly reinforced section, we have a higher ultimate curvature, so we have a more area under that diagram, which means an increased energy absorption and energy dissipation. Finally, adding compression steel makes our section easier to construct. Shown here is an inverted T-beam that I built while at the University of Texas. You can see the dense reinforcement cage. Having the compression steel allowed for this cage to better be tied together so that we could assemble it in one location and then move it into the forms and make sure that all the reinforcements stayed in the same location. So here we can tie the reinforcement or tie all of our shear reinforcement and the rest of the reinforcement in the cage at the bottom and the top, which just gives us a sturdier cage. Next, we're going to go through an example problem where we compute the curvature ductility for a singly reinforced and doubly reinforced section. You can see this is the same section that we looked at in previous examples, where we have a 12-inch by 20-inch width. We have 3 number 8 bars as our tension steel in both sections, and 3 number 6 bars as our compression steel in our section considered for Part B. We'll have the same concrete strength for both sections, F prime C of 4 KSI, same grade 60 steel with 60 KSI, yield strength, same cover, same diameter ties, and we'll say that we computed a usable epsilon C max of 0.0038. We know from before we have our 2 curvature ductility values, so one the exact and one an ACI approximate of a curvature ductility of about 5 and about 4 for our singly reinforced section. We can find the exact curvature ductility using any type of a computer software that will do this analysis. If you're taking my my course then will use an Excel sheet software called Reconnaissance that I'll provide, and we can use this to find an exact curvature ductility value of 5.22 for our section B. We can also find our curvature ductility using ACI approximations. In this case, we start with our tension equal to compression, our equilibrium, where our only tension is our tension steel, ASFY, and we have our two compression components, our compression steel, AS prime times FS prime, and our compression block component, which is the same as a singly reinforced section. We're going to assume that our compression steel doesn't yield, which is most often the case, and we'll use a linear strain profile to relate our stress in our compression steel to our compression block depth C. We can plug in this F prime S expression into our equilibrium equation, which we do here, and we can simplify it down into a quadratic, where we have an A times C squared plus B times C plus a C component equals 0. And then we can just use a quadratic equation to solve for C. If we plug in all of our known values, we can calculate the A, B, and C components in our quadratic equation. So we can calculate our A, B, and C and plug them in and solve for our C. So in our case, we'll get a C of 3.15 inches. We made an initial assumption that our compression steel didn't yield, and we need to check that assumption. We can go back and use this C equal to 3.15 in our equation for the stress in our compression steel and calculate and find our stress in our compression steel, Fs prime, to be equal to 24.9 KSI. This is less than 60 KSI, which is the yield strength for this steel for a grade 60 reinforcement. So we know that our initial assumption was correct. We can then find our nominal curvature, which is just the ratio of our assumed compression strain in our topmost compression fiber here, 0.003, which is our ACI assumption, divided by C, which we found to be 3.15. And then in this case, we see that our nominal curvature is equal to 9.52 times 10 to the negative fourth radians per inch. On this slide, we find our elastic behavior, including our compression steel. This is the same analysis that we did for a singly reinforced section, except now we have an additional component for our steel that's above our neutral axis. We have the area of our compression region here, B times KD, times the distance from the centroid of this region to our neutral axis here, KT. So that's KD over 2. Then we have the area of our compression steel, so N prime minus 1 times AS prime, the transformed area, times the distance from the centroid of this compression region to the neutral axis of our section, so KD minus D prime. And then we have our steel component, so N times AS, the area of our transformed tension steel, times D minus KD. So D minus KD gives us this distance here. We can then simplify all of this and solve for KD. Again, this will be in the form of a quadratic. And in this case, we'll find the KD depth equal to 5.7 inches. We can then use our KD in our expression for our yield curvature. So we're finding our yield strain, which is just our yield stress divided by our steel modulus, and then divide this by D minus KD to give us a yield curvature. We can then plug in our yield curvature and our nominal curvature, which we found on the previous slide, to calculate our curvature ductility, which in this case is equal to 5.5 using all of our ACI approximations. Here we can see the comparison between our singly reinforced and doubly reinforced section. You can see that our doubly reinforced section, we're going to have an increased ultimate curvature, which will increase our curvature ductility, both in using computer software and also using the ACI approach. We can see in this example, we're going to get some more pronounced benefits when we use our ACI approximation. But in general, adding compression steel is going to increase our ductility. Next, we're going to look at how confinement will affect our moment curvature behavior. We can see that our confinement is not going to impact our behavior until our epsilon c exceeds the value when our unconfined concrete begins to spall off. We can remember that our confinement is only going to affect the effectively confined concrete, so all the other concrete is going to spall off. Here you can see that our compression zone is going to be above our neutral axis, so the region contained by our compression block. And after we lose our cover concrete, our neutral axis is going to change. So our compression zone, we're still going to need to satisfy equilibrium, tension equal to compression. So this area here is going to change so that our compression can still equal our tension. This means that our moment curvature curve is going to have two stages, before and after our cover spalls off. Before our cover spalls off, we're just going to have a moment curvature behavior like we did, not considering confinement. Then at some point, we're going to have our cover spall off, and we're going to transition from our initial moment curvature curve to our confined moment curvature curve. And then you can see we'll increase and have some additional ductility and additional curvature that we can achieve because of our confinement effects. Shown here is the moment curvature behavior for the section that we've been investigating on the past couple slides. We see initially our initial section performance, and then we see the confined moment curvature section performance for a section with number 3 ties spaced at 4 inches and a section with number 3 ties spaced at 24 inches. You can see that when we have closer spaced ties, we'll have more benefits from confinement. Our concrete will be more effectively confined, so we'll be able to achieve a higher ultimate strength and more ductility. On the next slides, we're going to look at how we can calculate our short-term and long-term deflections for our reinforced concrete members. First, we can remember our basic mechanics of materials relationships relating moment to curvature and then curvature to deflection. As an example, here is the moment diagram for a simply supported beam with a distributed load. We can use this moment diagram with our moment curvature relationship for our section to determine the curvature diagram along the length of the beam. We can then remember that our deflection is related to the area underneath our curvature diagram. So what we can do is we could discretize our curvature diagram along the length, and then we can use moment area theorem to find the deflections at midspan. So I'm not going to go through this process in depth in this class, but this process would be applicable outside of the linear elastic range. So we could find our ultimate deflections using this procedure. Typically, when finding short-term deflections, we're going to use linear elastic assumptions for our concrete and use a modified moment of inertia based on our uncracked and cracked section properties. So something similar to the expression shown here, where we have some modifier times WL squared, or L to the 4th, divided by EI, where our E will just be our modulus for our concrete, and our I is going to be this effective moment of inertia. So this is the procedure that ACI 318 uses. ACI allows us to use an effective moment of inertia depending on our loading. We'll do this by first finding our gross moment of inertia, our crack transformed moment of inertia, and our cracking moment using this equation here. Then we can calculate our maximum moment in the member due to service loads, our M sub A, and we can use that M sub A to determine where we are on our diagram here to the left. So if our section is not yet cracked, if our M sub A is less than our M cracking, then we're going to use our gross moment of inertia. If our section is, or if our MA is above cracking, then we can use our 318, ACI 318 expression for the effective moment of inertia. So our effective moment of inertia we can find using this equation. So as our M sub A increases, our I for our section is going to decrease and approach our I crack transformed. Note that different applied loads are going to produce different effective moment of inertias. If we have a W1, this W1 is going to cause some MA or an applied moment that's associated with that W1, and we'll use this I effective to calculate our deflection associated with W1. This means that if we have another load, we need to use that load to calculate another I effective and use that I effective to calculate another deflection. Because every load is associated with a specific stiffness, which we then use to find a specific deflection associated with that specific load, if we are looking for a change in deflection between two loads, we need to first, say here we want to find the difference in deflection between delta 1 caused by W1 and delta 2 caused by W2. We would need to find the deflection associated with W1 first, and then find the deflection associated with W2, and then find the difference between those two deflections. So the deflection caused by W1, the deflection caused by W2 with their effective moment of inertias, and then find the difference between the two. Just note that this isn't the same as just taking W2 minus W1 and using another I effective for one of those loads. ACI has two different ways that they'll account for these different deflection limits. The first is a minimum thickness requirement. We can see that the minimum thickness requirement is actually a deflection limit by the derivation shown on this slide. Let's say that we have some deflection limit, which is delta over length, needs to be less than some constant C1. We know that our deflection is will generally be related to our load using something like this expression, and we can plug in our delta here, so to get this expression here. We know a lot of these are constants, so we can simplify this expression to an L cubed over T cubed times another constant C2. So we can see that this thickness needs to be, in this case, or L over T needs to be less than some constant C1. So this is just showing you that the minimum thickness requirement is just another way, or it's just another way to show a deflection limit. ACI has a minimum deflection limits based on element. So shown here are the minimum thickness, or the minimum thickness requirements based on element. So shown here is a minimum thickness requirement for non-pre-stressed one-way slabs. Depending on the support conditions, we have different minimum thickness requirements. And also here we have the table for minimum depth of non-pre-stressed beams, depending on our support conditions. So if we don't want to check deflections, we can just make sure that our members have at least the minimum thickness shown in these tables. If we don't meet our minimum thickness requirements, then we need to meet our deflection limits, which are shown in this table. For different members, different conditions, and given what deflection or what loads we need to consider in our deflections. And then with all these, we have our different deflection limits. We'll note here that deflections are a serviceability concern. So we use service loads, which are our unfactored loads, to calculate our deflections. Creep and shrinkage are going to impact our long-term deflection behavior of our flexural members. So we need to be able to account for these long-term effects. First, we have our shrinkage is going to cause shortening of the beams, and our tension reinforcement is going to restrain that shrinkage. So if we have an initial strain, our shrinkage strain is going to be greater at sections without our reinforcement and less where we have our reinforcement. You can see that this curvature caused by our shrinkage is going to increase or amplify our deflections. Our positive moments, which are going to be on our beams, are going to cause the top of our sections to be under sustained compressive stress. This is going to cause creep in the top of our sections. And again, our reinforcement at the bottom is only going to decrease any creep effects on the bottom of our section, but not the top. So we're going to have creep due to our compression stress in the top of the section, and this is going to increase or amplify our deflections. Note that when we add compression steel, we're going to restrain this creep, and it's going to decrease these creep deflections. We can calculate our long-term deflections using the effective modulus, just like we did before. We can remember that our effective modulus is just our modulus of our concrete divided by 1 plus our creep coefficient. If we plug this into our long-term deflection equation, we can see that our long-term deflection relates to our short-term deflection by 1 plus our creep coefficient. If we calculate our creep coefficient, we can use this approach, but ACI allows us to use a simplified approach where we have this lambda t factor. And this lambda t factor amplifies our short-term deflections to take into account our long-term effects, and it allows a reduction based on the presence of compression steel. These expressions are based on work by Yu and Winter in the 60s. ACI only accounts for elastic deformations, but there is additional ductility that beams will have. So we're going to look at these deflections using a cantilever beam. Looking at deflections that happen after our elastic region and into our plastic region. So here we have a cantilevered beam with a moment diagram. So our moment's equal to PL at the ends, and we have a point load at the end. So we're varying linearly up to a zero moment at the end of the cantilever beam. We're going to assume in this section that, or in this initial explanation, that we have elastic plastic behavior. Where our plastic behavior, we have a moment equal to my, which starts at a yield curvature phi sub y. And until the start of yield, our load deflection response is going to be elastic. And we can find our deflection then using our moment area theorem. And we just find that our deflection is equal to PL cubed over 3EI. When our section reaches my at the end, we're going to have a plastic hinge that begins to form at the end of the beam. If we assume elastic plastic behavior, the hinge is going to form right at the end of the beam. So our strains are all going to be localized at the beam end. There's actually going to be some strain hardening or a strain hardening region. This means that the plastic hinge is going to have a certain length. which I highlight here. So we have a hinge forming over a certain length. We can then idealize this behavior as an elastic response, which just takes us up to our yield curvature at the end, plus a plastic response, which is shown here with this rectangle, being with its height being the difference between the ultimate and the yield, and the length being the length of our plastic hinge. We can then find our total deflections again from these curvature diagrams using our moment area theorem. And we'll eventually find that our deflection is just equal to our elastic deflection plus our plastic deflection, which is equal to our plastic rotation times L minus half of the hinge length. If we assume that L is much greater than our hinge, then we can just have our deflection equal to our elastic deflection plus our plastic rotation theta p times L, the length of our cantilever beam. Our rotation can be determined by integrating our curvature over the hinge region, shown here. So we can find our plastic rotation. Our rotation is going to be dependent on if we have good curvature ductility, if we have a delay of buckling of our longitudinal steel. So we need some kind of lateral support, normally provided by our shear stirrups and ties. And then also a delay of shear deterioration in the hinge region. Our hinge region needs to be able to hold up even under shear loads. To find our rotation, we need to specify a combination of our ultimate curvature and our hinge length. And for this section in this class, we're going to use an approach established and developed by Maddock and Corley in the 60s, where we can find a plastic hinge length dependent on the depth of our tension steel and the moment gradient, so D and Z. And then our ultimate stress is dependent on our moment gradient, our compression reinforcement ratio that accounts for our transverse steel and our compression steel, and Fy and our B. So this equation will take into account confinement effects, and which increase the ductility of our concrete. In this example problem, we're going to determine the plastic rotation for the cantilever beam that's shown below. We're looking at the same rectangular section that we've been looking at in this section with 3 number 6 bars on the bottom in compression and 3 number 8 bars in tension. So note the section's flipped because in our cantilever beam we have tension in the top. From before, we saw that our yield curvature is equal to 1.73 times 10 to the negative 4th radians per inch. We're going to use both a theoretical approach, and then we're going to use the equations and procedure developed by Maddock and Corley. This section was analyzed before using moment curvature software, and we found that the ultimate curvature is equal to 0.007. We can calculate or approximate our plastic hinge length as 0.5 times D. So this is a simplification to find an approximated plastic hinge length of 8.82 inches. And then we can plug in and calculate our plastic rotation. Our ultimate curvature minus our yield curvature, which we found for the section before, times our plastic hinge length to get our plastic rotation of 0.06 radians. You can now pause this presentation or just mark where we are and go to the example problem where we go through the Maddock and Corley approach for calculating the plastic rotation of this section. In this next short example, we're going to determine the plastic deformation of the cantilever beam shown below. This is the same section from the previous example, so we already have the plastic rotation capacity calculated. So it'll be easier to do this example. We can find our plastic deformation by either removing the hinge length, which would be a more exact approach, or not removing the hinge length. In this case, removing and not removing the hinge length is easy, but with different support conditions and loading configurations, it can be a little more tricky. So this will just show you that removing the hinge length and just considering the beam length is a reasonable approximation. So you can see here our deflection is equal to our elastic deflection plus our plastic rotation times L minus the hinge length over 2. So here we can find, we calculated our plastic rotation in the previous example, so we just use that, and we can find our deformation here, our plastic deformation, equal to 4.73 inches. When we remove the hinge length, we'll get a plastic deformation of about 5 inches. So not removing the hinge length is a reasonable assumption, and we can use it with more complex geometries. Here is a load deflection curve for our section. So you can see at the end of the elastic range, we have a deformation of about 0.83 inches. At the end of our plastic range, we're about at 5 inches. So if we ignore our plastic deformation, we're missing out on about 4.1, 4.2 inches of deflection capacity, which is beneficial for load redistribution and when we're considering a seismic or other extreme loading. In this next example problem, we're going to calculate the plastic capacity and plastic deformations for the members shown below. So we're going to conduct a plastic analysis on this section, like we did in our first section, our first module of the course. Our section is a 12-inch wide by 24-inch high, doubly reinforced section with equal compression and tension reinforcement. We have 4 KSI concrete, 60 KSI yield strength steel, grade 60 steel, and we're given our cover and our tie area. And also we're given the spacing of our ties. We're given our yield and ultimate values, which we found from procedures before, and we'll use these values within our example problem. And our support conditions, we have it's a fixed beam with a 24-foot length. So at this point, you can pause the presentation again and go to our example problem where we work through this example. Our final example problem is looking at a flexure test that was conducted on a beam shown here at the University of Texas. It's a simply supported beam with 2 point loads where we have both compression and tension steel, so 3 number 11s on both the top and the bottom. And we have no transverse ties in our moment region, so no shear reinforcement in the moment region. And in this example, we're going to calculate the nominal capacity of the section, the first cracking load, and also the load deflection relationship. So you can exit this presentation and go to this final example problem. Shown here is a list of resources for further study on the flexural behavior of reinforced concrete members.